itself, it's a subject that's really disappeared from physics departments. It's mostly studied in chemistry departments these days, although it's, of course, a problem with quantum mechanics, but, you know, chemistry is applied quantum mechanics. And some parts of physics have kind of been sloughed off, like, you know, electrical circuits, electrical engineering, you know, solid state physics, and material science, what have you. So most of what we'll talk about in the next couple of lectures is what's really these days called quantum chemistry. And so if you want to really study the real details of how one, from first principles, calculates the energy levels and structure of atoms and molecules, you'll find it in books called quantum chemistry. So part of that prelude means that, you know, I don't really know this stuff that well myself, but I want to, because it's not something I've ever done for a living. You know, I want to just make a little plug here. There's a lot of discussion these days in the press about higher education and, you know, state budgets and what one should be doing with the cost of higher education. You know, what distinguishes higher education from secondary education is that people like myself who are trying to distribute the knowledge are people who try to create the knowledge. And so I can come into the class and do the class because it's what I do for a living and I know it. I don't have to read it in a textbook and figure it out and then tell you. The point of the problem is that if it's not something I do for a living, it's a lot harder for me to really, really tell you what it is from my heart. And this is not something I do for a living. But nonetheless, I have some ideas about it and we'll do our best to share some of that with you. Okay, with that preface, let's discuss where we are and where we're headed. So we're talking about the energy levels of atoms, and particular atoms with more than one electron, where things start to get complicated and interesting. So the simplest case of that is two electrons, helium or helium-like atoms. That's what we've been talking about for the last week. And from the most basic perspective, the dominant forces are the electrostatic forces. So we have the attraction of the electron, each of the electrons to the nucleus, which has some atomic number Z. This is in atomic units, dimensionless. And then we have the repulsive energy between the two electrons. And we, for example, discussed that one of the ways to approach trying to look for, say, the ground state of the atom is to try to use some physical intuition to parameterize the solution in some way, and then use the variational principle and the fact that the true ground state will always be less than the expectation value of whatever wave function you choose, and just try to minimize that expectation value with respect to some parameters. And so, for example, what we discussed last time is that we can think about each electron moving independently in a potential that is that of the nucleus and the screening effect of the other electron. Okay? So that approach is very powerful, and you have some homework problems this week to look at the variational approach, for example, in solving for the energy levels of diatomic molecules to get a little bit of feel for how that might work. But this leads us to this idea of the effective potential is really at the heart of the core structure and the basic structure of atoms and molecules that underlies chemistry. The idea then is to somehow, as we will discuss in more detail and in more quantitative detail today, think about how we can think about the potential seen by each electron, which in this more general case for more than 2 electrons would be the attraction to the nucleus and the repulsion from all the other electrons in the atom. That somehow, some way, think about whether this is a reasonable approximation, could be written as some spherically symmetric screening potential and then corrections. Okay? So the idea is that all the other electrons, other than the one electron of interest that we're looking at a time, produces some kind of spherically symmetric electron cloud that shields the nucleus. That shielding potential is a function of position. And that changes the 1/r attraction to the nucleus. Okay? So if we can ignore these other effects, then we have a kind of separable Hamiltonian. It's not exactly separable, it's a kind of self-consistent separable Hamiltonian in the sense that this screening depends on all of the other electrons. So we're going to have to think about what this really means. If we want to, right now I've just written down some stuff, nothing's been derived. I just said, hey, let's just pretend this is true. We'll get to that in a moment to try to get this more systematic. But for the moment, let's just, take this as a given, that this is a good approximation. In which case, what we have is an effective, this is what's called the central potential. That's to say, it only depends on the distance from the origin and not the direction. And when we have a spherically symmetric potential, we know that we can write the energy levels in terms of a set of good quantum numbers for each of the electrons, assuming there's an effective potential for each, the same central potential for each of those electrons, in particular energy. And so each electron is specified by these good quantum numbers, N, L, and M sub L, and if we want to include spin, M sub S. So far in this description, we haven't included the spin, other than, as we'll discuss, the quantum statistics, which are important, as we've discussed. But these are what we call electron orbitals. Now, a very important thing to note in this description is that this is not a 1/r potential. It's a spherically symmetric potential, but the force doesn't fall off like 1/r. As we discussed, one kind of picture of this for the case of the 2 electrons is we can imagine that as a function of r, if one of the electrons is very close to the nucleus, it's not very shielded, in which case it feels the full force of the nucleus, and in this case, we'll say charge 2 for helium. Then it would fall off like 2/r. Whereas far, far away, that electron is fully shielded, or the nucleus is fully shielded by one of the other electrons that falls off like 1 over r, and we might imagine some kind of interpolation between them, and this would be our effective central potential. This is not a 1 over r potential. And because it's not a 1 over r potential, it doesn't have that accidental symmetry that we discussed in the first week of lecture associated with hydrogen, whereby the energies only depended on the principal quantum number. In general, they depend on both the principal quantum number and the angular momentum quantum number. In fact, it's better generally to write this in terms of a radial quantum number and a angular momentum quantum number, but it's traditionally written in terms of the principal quantum number. So again, to emphasize, what this means is that if I look at my potential as some kind of, whatever it is, not necessarily 1 over r type thing, that's just an exaggeration, but let's just look at it like that. This is the bare potential, and then of course we have the angular momentum barrier. To give us this, oops, I got to trip over this at least once a lecture to remind myself that it's there. We need a better solution. The total potential now, in this case, has some kind of form with an angular momentum barrier. So that generally the energies are going to be very dependent on L. It's only a bizarre accident, which is not bizarre. It arises from, as we discussed, some geometrical symmetry, which you can think about as SO4 symmetry that was associated with the 1 over r potential. But generally, the energy will depend very strongly on this angular momentum barrier, because the amount by which, how close the electron, one electron can get to the nucleus, will depend on this angular momentum barrier. So that we expect, generally, better shut this off before it goes off, that the energy for a given n, the energies associated with lower angular momentum barriers will be more deeply bound, because then it can get closer to the nucleus. So the smaller L for a given n are more deeply bound. And this is not a small effect. This is not like a magnetic effect or a relativistic correction. This is a huge effect. This is why, other than in hydrogen or hydrogenic atoms, do we have anything close where the different orbitals have near the same energy? They have nowhere near the same energy. And you build up from the lower L's up to the higher L's. Of course, there's still the degeneracy in M sub L, because this is spherically symmetric. That's an SO3 or SU2 type symmetry, rotational symmetry in 3 dimensions. And then we could add in magnetic effects and fine structure in order to think about, and we may talk about that next lecture in terms of the fine structure for higher number of electron atoms. So with this kind of picture, what we have is you know, this picture of the central potential leads to an explanation of the periodic table. I mean, the periodic table was an empirical assignment of the elements which periodically had kind of the same chemical properties. We understand that today, and we've understood that for 100 years, almost, or whatever it's been, close to it. Which is really not that long in the grand scheme of things. I mean, you might have a grandparent who's 100, maybe. So, you know, it's a human scale. In terms of the filling up of orbitals as we increase the number of electrons, right? So we talk about the configuration, electron configuration, whereby we fill up according with the Pauli exclusion principle. So, you know, we have our standard kind of thing. We have hydrogen, the configuration is 1s, helium, 1s squared, lithium, 1s squared, and then we fill in the next orbital, 2s. Beryllium, I don't remember the periodic table, I should, boron, et cetera, et cetera, et cetera. Neon is the helium, and then we have 2s squared, and then we have 2p6, and then sodium is neon with 3s, etc. And of course, you remember from your high school chemistry that we call the configurations with 2l plus 1 electrons times 2 for each spin state in a given L as a closed shell. And if we have electrons in open shell, we call that the valence electrons. Now, as you also may remember from your high school chemistry or whenever last time you studied chemistry, that in fact, this filling up of orbitals has some, in terms of, you know, if we just thought about this from the point of view, first take a principal quantum number, start with the lowest L, fill up those orbitals, take the next L, fill up those orbitals, go up to L equals n minus 1, and then go to the next principal quantum number. That actually, at some point, doesn't work. And what is it, after calcium, so calcium is the neon configuration, and then it has 2 electrons in the 4s orbital. But then scandium, which next you would say is 4p, is actually 3d, is next. So as you remember, you have these weird rules that sometimes you fill in the orbitals with lower principal quantum number but higher angular momentum, or whatever they were called. Eventually these get filled up and then you fill in the 4p. So the 3d orbital has less energy than the 4s. It's higher energy than the 4s. The reason for this is the competition between the energy associated with different radial confinements and the angular approach, that is to say the impact parameter or the angular momentum barrier associated with the electron getting close to the nucleus. There's a competition between those. Both of those raise the energies, and so you get this kind of different ordering. Yes, sir?
What's actually the reason why we still have kind of the same orbitals as hydrogen? Because we always use the same quantum numbers, although the orbitals are of course influenced by the other.
So these are not the same, they're not hydrogenic orbitals, but they have the same basic quantum numbers because of the form of the Hamiltonian. So if each electron, if we recall the Schrödinger equation associated with this Hamiltonian, let's just write it down again, just to remind ourselves. So for a given electron, we're in this picture of, as we'll discuss in more detail quantitatively in just a moment. But this is a kind of single electron Hamiltonian. Each electron sees this potential and has a certain amount of kinetic energy. So our for a given okay, now this is equal to the radial kinetic energy plus the angular kinetic energy plus, and this only depends on the magnitude. So this is the general form of the Schrödinger equation, where this is not a hydrogenic potential. If it was hydrogen, it'd just be 1 over R. But it's this, but it's now some more general central potential. And this, as we said, we can separate it into radial and angular coordinates. However, the radial wave functions are not hydrogen's radial wave functions. The angular part, well, that's the same. So we separate this into a radial wave function, which will have, a radial quantum number, and it will depend on L and Y, L, N of theta and phi. So because of the central potential approximation, these are the good quantum numbers. But the way in which the energy depends on R, n sub r, or the principal quantum number, which is n sub r plus L plus 1, is not the same as for hydrogen. For hydrogen, this was just 1 over L squared independent of L. In this case, it would be very different. Okay. One thing that we've written down this configuration if we wanted to write down what the wave function is, or the state of the multi-electron system in this kind of configuration, we need to take into account the identical particle statistics and the complete antisymmetry of the multi-electron state under exchange of any two electrons. And there's a number of ways to do that. We could use what's called second quantization to do that. And that's what's more typically done these days in thinking about many-body physics, is to work in terms of creation annihilation operators that create and annihilate fermions in a many-body state. But we could do it in a first quantization way by somehow taking into account every minus sign that comes under exchange. And I just want to introduce, it's just something you'll see, you may hear about, the idea of the Slater determinant. Is that something you've ever heard of? The term Slater determinant? Maybe heard of it, but you should know what the Slater determinant is. So the idea is we want to, we have an electron configuration, meaning that there are electron orbitals, including the spin. So let me let phi alpha be a shorthand for the state with some spatial orbital and then some spin state. Okay, so this could be up or down. So this is some particular member of a basis of electron states, which includes both a spatial orbital as well as a spin state. Now, if we want to write down a multi-electron state or wave function which had one of the electrons in an orbital phi alpha, another one in phi beta, another one in phi gamma, etc., 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 we need to antisymmetrize to know which electron is in which of these states. So one writes that using the properties of the determinant, because you remember the determinant is antisymmetric under the exchange of either its rows or its columns. So we can write down the wave function associated with n electrons as all possible permutations. So there are n factorial permutations of these orbitals. So we have to divide by 1 over the square root of n factorial to normalize it, times the following determinant. Okay, so this is a multi-electron state where one of the electrons is in state phi alpha, another one is in phi beta, another one's in phi gamma. And then I permute over all possible electrons being in every possible orbital, and then take this determinant. Now, clearly this obeys the Pauli exclusion principle. Because if phi alpha equals phi beta, and remember phi, as in this notation, includes both the spatial and spin state. So if any of these, if either of any of these columns are the same, the determinant is 0. So this obeys the Pauli exclusion principle. Okay. Now, just let's write this out for the case of, say, 3 electrons, like the lithium case. What does this represent? So let's say, for example, lithium. So let's say phi alpha is equal to the 1s orbital and then spin up. Phi beta is a 1s orbital with spin down, and phi gamma, for example, is a 2s orbital with either spin up or spin down. Both of them would be a degenerate state. Let's just take that as our 3 orbitals that will then make a configuration out of that. So now let's look at all 3 electrons. So I have 1 over root 3. I have take that determinant. So that's equal to 1 over root 3 alpha 1 times beta 2 gamma 3 minus beta 3 gamma 2 minus beta 1 oh, there's a 2, yes, sorry, thanks. It's a 6 and this is a 2. Gamma 3 minus alpha 3 gamma 2 plus gamma 1 times alpha 2 beta 3 minus alpha 3 beta 2. Right, so for example, this first term over here is, we have a 1, I'll put a 1 over root 3 times the u to, with spin up, let's see, R2, 2s, R3 minus 1s, R3, 2s, R2 times electron 1 is spin up, and then we have another term where this is plus, sorry, this is plus, this is minus. In other words, we end up with this, again, the singlet triplet pairing. If I have triplet spin that's coupled to either antisymmetric space, and if I have singlet spin that's coupled to symmetric space. For the case where the two orbitals are the same, where alpha and beta are the same orbital, for example, in this case, which is over here, we only have the singlet pairing of the spins. This is tedious. This is tedious beyond belief. We wouldn't write out the Slater determinant if we could avoid it, which is one of the reasons why second quantization is much more useful. In other words, I could, in the second quantization, which I'm not going to get into in any detail, but just to mention, I could write the state that I just described as involving creating 3 electrons out of the vacuum, where one of the electrons is created in alpha, one of them is created in the beta, one of them is created, right, this would be my 3 electron state. And the antisymmetry of the wave function under exchange is taken into account by the fact that these two operators that create electrons anti-commute. That's to say, if I switch alpha and beta, pick up a minus sign. This is what's called anti-commutation relations. Because they don't commute, they anti-commute. It's much more tractable to deal with multi-electron systems in the second quantization formalism than writing down Slater determinants. But you'll see, so we'll talk about this a little bit now. Okay.
So to get the true state, you would still need to sum over all permutations of orderings? Or is that somehow applied?
What do you mean, in the second quantization?
Yeah.
No, this is all of them.
Okay.
This is all of them. This doesn't, if I wanted to write down the wave function, this is a sort of a Keck formalism. If I wanted to write down this as a function of R1, R2, and R3, then what I would do is I would look at the field operators which annihilate an electron at a position rather than in an orbital. Act this on the state, and then take its projection on the vacuum. And because these guys anti-commute, that is the Slater determinant. If I had a multi-boson system, I could do the same thing, but instead of having anti-commutation relations, I would have commutation relations. I mean, to really get into this, to do a little bit of many-body physics and quantum field theory would take us more time than we got. But I just wanted to alert you to the fact that you don't have to deal with Slater determinants. You guys just saw how it's annoying it is. All right. So we have this core structure. But we didn't really justify it in any way except maybe a little bit intuitively that, well, the electron shields us in some kind of of spherically symmetric wave function that shields out the nucleus. But how do we get, how would we find what that spherically symmetric shielding potential is? And we could try the kind of variational approach that we just discussed, and that's certainly one way to go about it, but we could be a little bit more systematic about it. Before I do that, let's just back up for one moment and just think about what we're doing here. Why don't we just solve the Schrodinger equation? I mean, I wrote down the Schrodinger equation with some Hamiltonian. Why all of a sudden did I get these complicated things of shielding potentials and, some kind of spherically symmetric central potential approximation? Why don't we just solve the Schrodinger equation? I mean, after all, at least in this, even if we ignore the fine structure, and we don't worry about spin-orbit coupling and all of that, our Hamiltonian was pretty simple. The Hamiltonian that we wrote down, it was the sum of single particle Hamiltonians and this repulsion, where this was the hydrogenic Hamiltonians. So why can't I just say, well, let's look for H on psi is E psi, and just solve it?
It's more difficult than it seems. You just can't separate it.
That's right. It's not separable. And we can try then to think about some kind of representation of psi in terms of some basis, and then look for the solutions to the coefficients of psi in that basis. Right? So I mean, generically, psi is, let me just call these basis vectors n, although it's not the principal point number, it's just some number, right? And then maybe we have the continuum, so we have discrete So I might have some basis representation. For example, we could use hydrogenic wave functions. They span the space. So I can say there is a basis of every electron is with proper symmetry, is in one of the bound states, or maybe it's unbound. Write down a multi-electron wave function in terms of all of those orbitals, and then just plug that in and solve it. Why is that so hard? Well, what you see here is, even if somehow I said the contribution to the states are dominated by the bound states. That is, say, only the bound states of hydrogen are the ones that are in the basis that represents the bound states of lithium. even if I did that, even if somehow this, I can ignore this, and I asked them, and I just use this basis. If I have a multi-electron system, if I take d basis vectors for each electron, how many basis vectors do I need for n electrons? D to the n. So the number of basis vectors grows extremely rapidly. Just brute force trying to diagonalize this is going to be incredibly difficult and typically not possible, especially as n gets big enough. Of course, then I have the added difficulty of making sure that everything is consistent with the anti-symmetry of the wave function. And that's why this problem is really just not tractable to do in any kind of exact way. The whole business of quantum chemistry is about choosing the right basis vectors to get d as small as possible. Because of course, in this, even if I take the discrete spectrum, what's d here? It's actually infinity. There's an infinite number in the Rydberg series. Even if I truncated and didn't include the continuum, d is infinity here. So it's really a question of the whole art of quantum chemistry is choosing the right subspace, the right set of basis vectors that effectively capture as much of the probability amplitude as possible, but not too big, so that one can do this numerically on a pretty good computer. So if this exact solution is going to be so hard, we look for some approximation methods that, and we'll have to think about how good they are. And the first approximation method is essentially to, instead of choosing some superposition of orbitals within a basis for each electron, to assume that there is essentially one orbital for each electron. That's to say, one starts with some kind of single Slater determinant, or picture like this, where I've created one electron for the n electrons. Each electron is described by a particular orbital. So it's kind of this separable approximation. It's not really separable because of the anti-symmetry, right, that we have to impose. But basically, it's assuming a separate orbital for each electron. And that's what's known as the mean field approximation. So let's discuss that. So the mean field approximation each electron sees the potential of the nucleus and the average effect of all the other electrons. And then we distribute the electrons self-consistently in a way that I'll describe in a moment. In separate orbitals to minimize the energy. So this mean field approximation is also known as the self-consistent potential, and it goes by the name of Hatree Fock approximation. So Hatree, back, I don't know, in the 1920s, wrote this down originally as a kind of talking about a self-consistent potential, but didn't properly account for the anti-symmetry of the wave function. And then Fock and Slater came along and fixed that, and it's now called Hatree Fock. And it's now in the context of more sophisticated many-body physics, one term in a series of Feynman diagrams that one would write down in terms of all possible interactions between the electrons. So it can be understood as a controlled approximation, which this is the lowest order approximation. So how does that work? Well, the idea is to take as an ansatz the state of the system is given by a Slater determinant. Or equivalently, each electron is in its own orbital. I don't know which one it is. So it's kind of the base approximation with the Fermi statistics to separable wave function. One wave function for electron 1, another wave function for electron 2, another wave function for electron 3, etc. Properly anti-symmetrized. We take that as an ansatz, and we're going to look for the solutions for what those orbitals need to be in order to minimize the energy. So that's what we're going to do. Let's do it over here. So here's our Hamiltonian. So take as an ansatz it's a Slater determinant for n electrons. Minimize the expectation value of the Hamiltonian with respect to orbitals. So we want to find the orbitals that minimize this energy when psi is of this form. And that is the self-consistent solution. And as we'll show, under some conditions, it's rigorously a central potential. If we have, for example, a closed shell. So just to get a little bit of a handle on this, let's start with just 2 electrons, just to see what the hell it looks like. So we take as our state for the 2 electrons this Slater determinant. It's not a matrix, it's a determinant. Okay, and now we want to look at the expectation value of this Hamiltonian with this state. So let's do that. Let's write this up here. So our energy as a function now of this state, right, is the following. Write it all out. So I have the energy, remember H1 here is the single electron attracted to the nucleus Hamiltonian, the hydrogenic type Hamiltonians. And I can have particle 1 or particle 2 in, or electron 1 I should say, or electron 2 in orbital alpha or beta. And then I have the repulsive terms, which look like this. Let me write them down, and then we'll discuss what they mean. Minus Okay, so this came from writing the state out, 1/2 alpha 1, beta 2, minus alpha 2, beta 1, over root 2. That's the Slater determinant. I took this state and I took the expectation value here where this Hamiltonian acts on each electron independently and the repulsion acts on the 2 electrons in pairs. And we have all these terms. All right, so what we notice here, of course, is because, this Hamiltonian is invariant under exchange of particle 1 and particle 2, that we have double these terms, right? So this energy is the same as that energy. And this energy is the same as that energy, right? And same thing here. So I can get rid of these halves over here. And write write this in terms of the two energies so we write it over here. I'll write this out. My energy as a function of the state is the sum over the two orbitals. The zeroth order energy, the hydrogenic energy associated with each of those orbitals. And then we have plus a half lambda and mu equal alpha and beta, something I'll call J mu lambda minus K mu lambda, where E lambda is equal to that's the hydrogenic energy. And then J U lambda is this term. Which equals integral over the two electrons. Remember, I'm calling U the spatial orbital here, not the radial wave function. Sorry, let me call it okay, alpha beta is this. Let me write it down, and I will explain what this means. All right, let's discuss what this means. So the energy, the average energy, given this kind of two electron state, involves the individual energies, the hydrogenic energies associated with whatever that orbital is. There is this term and this term which have to do with the electron repulsion. This term is what we call, when we discuss this in the context of helium, the direct interaction. And we can think about that as the Coulomb energy associated with two charge densities. One charge density described, this should be each one of these guys is squared, excuse me. Charge density associated with the electron cloud psi U alpha. The charge density associated with electron cloud with distribution U beta. Those two charge densities are associated with the same charge, and so it's a repulsion. Then, in addition, we have this term, which is the exchange interaction. And if actually, I left off one important term here, which is delta M sub S alpha M sub S beta. Why is that? Remember that our notation here, phi, involves both the spatial wave function and the spin state. So when we take this inner product, well, in this case, it didn't matter what the spin states are, because I'm looking at the inner product that will involve the inner product. This thing is spin independent. So the spin part of the ket comes through the inner product, and we have whatever the spin state is of alpha goes away, whatever the spin state of beta goes away. On the other hand, in the exchange interaction, what we have is the spin state associated with one electron and the spin state associated with the other electron. And since this operator doesn't change the spin, this term only contributes if the spin states are the same. Which is to say that we reduce the repulsive interaction between the electrons by an amount having to do with the Pauli exclusion principle. If the two electrons are in the same spin state, then they can't get close to one another because of the Pauli exclusion principle. And therefore, the amount of repulsion between those two electrons is reduced. Sometimes that's known as the Fermi hole. That's to say there's a kind of, has to be a hole in the electron distribution, the way it's distributed in such a way that the two electrons can't be in the same place and in the same spin state. So we see the direct interaction here, and we see the exchange interaction here. This is a 1 and 2, and 1 and 2. Okay, so here's our energy. Now, in order to, what we want to do now is the variational calculation, variation with respect to the orbitals. So this is what's called functional calculus, which is to say, this is not a function of a single variable, but a functionale of a whole function. Now, to get into functional calculus takes a little bit of a while. I'm not going to do that. I'm just going to say some things, and you'll have to swallow it and read about it on your own, but I just want to give you a feel for it. There's one important ingredient here, though, that we need to discuss, which is our ansatz did not say anything about the spatial orthogonality of the wave functions. That's to say, the U alpha and U beta weren't necessarily, nothing in this ansatz assumed anything about the orthogonality of the U's. And we can look for the solutions whereby we think about these orbitals as independent but orthogonal orbitals by putting a constraint on our functionale using Lagrange multipliers. So we can use the method of Lagrange multipliers to constrain the orbitals to be orthonormal. Because otherwise it's not in any way clear that the minimum energy is going to be associated with these independent orthogonal wave functions. So we define a new functionale which is equal to this expectation value with a Lagrange multiplier. So we're going to put in Lagrange multipliers such that we simultaneously minimize over the orbitals and the Lagrange parameters, here written as E alpha beta. Okay? Have you seen Lagrange multipliers before in your classical mechanics? Same approach. Okay, now it follows, since this thing is equal to its star, when I do alpha, switch alpha and beta, that to keep this function all real, this is a Hermitian matrix. And therefore can be diagonalized. And so when one writes down the ansatz for the Hatree Fock, one assumes that we do that by a new set of orbitals which diagonalizes. It keeps, by the choice we'll make is the thing that diagonalizes this Lagrange matrix. Let's get rid of this junk. So, the idea now is to minimize with respect to the orbitals. We don't know what those orbitals are, we want to find the minimum of them. And so what we do is we take the derivative with respect to the orbitals in a way what's known as functional calculus. Actually, we can independently have to treat each of these, because they're complex functions, we have real and imaginary parts, or phi star. We look at the derivative of the function of the Lagrange function with respect to functional, with respect to the functions phi and phi star. And we want all these derivatives to be equal to 0. So, when we do that, let's look at one of these guys. We get the following. We get the derivative of this. If I take the derivative of this with respect to this function, well, the only term is when essentially this becomes a delta function, and I get this acting on that. So I get minus a half. This is, I know, pulling the rug over your eyes, but man, to do functional derivatives correctly would take us a while. I want us to just see what the Hatree Fock equations look like and their physical meaning, rather than getting into a bunch of math at the moment. Let me write this over here. So this is that first term, taking the functional derivative with the first term, just picks up that first Hamiltonian. Then I get the direct interaction. Yeah. And then I get the exchange. So let us just conclude here and just explain what we see here. What we have from these functional derivatives are for the two orbitals, phi alpha and phi beta, a set of coupled PDEs. They're coupled through this term, alpha and beta are coupled through this term, through the exchange interaction. Well, that's not quite true. They're also coupled here because the amount of shielding due to electron 2, which affects the repulsion with electron 1, is given by this direct interaction and by the exchange interaction. So these equations are, for these two orbitals, are known as the Hatree Fock equation. And it gives us the self-consistent solution, whereby each electron sees the attraction to the nucleus and shielding due to the other electrons, in this case, one other electron. That shielding is a combination of the direct term and then possibly a reduction due to the Pauli exclusion principle and due to the fact that the two electrons can't be in the same place at the same time if they're in the same spin state, which reduces the amount of shielding in some funny way. So we've reduced the problem to a set of coupled PDEs, and then you got to solve those things generally numerically. So next time what we'll do is we'll study a little bit more the physical meaning of these things. What is the nature of this energy, which came from Lagrange multiplier, which now is what we call the orbital energy. That's to say, each orbital has its own energy. The total energy of the system, though, is not just the sum of the energies of the individual orbitals because of the correlation effects that we've neglected. But we need to understand what these energies mean and in what sense this is equivalent to the central field approximation. And we'll finish that up on Wednesday. All right. Okay, we'll call it quits.